Hi students, good morning to all of you. This is Suresh, lecturer in chemistry in BRR GK Chammas Degree College, Palakollu. Today I'm going to start a final BSc 6th semester chemistry elective paper, analytical methods in chemistry, unit 1, quantitative analysis. So first, what is quantitative analysis? The name itself indicates quantity. That means how much of solute present in the given solution. That is what you have to determine, right? Again, this quantitative analysis is classified into two types, that is volumetric analysis and gravimetric analysis. So volumetric analysis, that is titrations. Again, volumetric analysis, there are four types of titrations we are having. That is, first one acid base titration, second one redox titrations, and third one complex titrations, and fourth one precipitation titrations. And the second category, that is gravimetric analysis. So volumetric analysis based on volume measurements, that is, they are performing titrations. And the second thing, gravimetric analysis, the process of gravimetric analysis, at the end of process you are getting yield. Based on that yield, weight of that yield, you are determining how much of solute present in the given solution. That is gravimetric analysis. Now I will discuss both, that is volumetric analysis and gravimetric analysis. In the first four sessions we are discussing about these four types of titrations. In the first session we are discussing about acid base titrations, right? First session we are going to discuss about acid base titrations. So what is acid base titrations? So there is a reaction between acid and base. So what is acid and what is base? So acid, which gives H plus ions in the aqueous solution, base, which gives OH minus ions in the given solution, right? So H plus from acid, OH minus ions from base. So these two are combined to form H2O, right? This acid base titrations based on the principle, that is neutralization, right? I will explain in detail. Right, so an acid base titration is a procedure used in quantitative chemical analysis to determine the concentration of either acid or base. So here we are determining concentration of either acid or base. So there are two types of acid base titrations actually, acidimetry and alkalimetry. So acidimetry, here we are determining a concentration, that is strength of base, by using standard acid, that is acidimetry. And alkalimetry, here we are going to determine strength of base, strength of acid, by using a standard alkali solution, that is base solution, that is alkalimetry. So, right, the two types of titrations, acidimetry and alkalimetry. In acidimetry you are using a standard acid solution for you determining strength of base. In alkalimetry you are using standard base for determination of acid, that means quantitative determination of acid. That is two types of titration, the two types of methods, acidimetry and alkalimetry. And the second point, the equivalence of acid base titrations is the point at which there is equal amounts of H3O plus and OH minus ions in the titration flask. Now what are the equipments we are required for this particular titration? That is a burette, a pipette, and a conical flask. Now in burette you are taking one solution, either acid or base. If in conical flask, pipette out another solution, that is acid or base. Now burette, for example, in burette you are taking acid, conical flask you are taking base. Now these two are reacting in a conical flask, acid from burette and already base in conical flask. These two are reacting and form an H3O plus H plus ions from acid and OH minus on base. They form water, that means neutralization, they are neutralized, right? Now here pH range and the change in color for some indicators. Now you need indicators, so you have to identify the color change, you have to identify the end point. So for end point you need pH indicators in acid base titrations. You are having different types of acid base indicators, and the first one, methyl orange, methyl red, bromethyl blue, and phenolphthalein. So acid methyl orange and methyl red, these two are acid indicators, because here you are having pH less than 7. So if you see the methyl orange, the pH range around 3.2 to 4.2, and methyl red also 4.2 to around 6.3. Now these indicators show different colors in different media. For example, in methyl orange shows red color in acid, and in base it shows yellow color. right? And phenolphthalein, if you say phenolphthalein is a base indicator because pH range in between 8.2 to 10.0. In its acid solution, phenolphthalein, there is no color, that is colorless. In basic medium it shows pink color. Okay, this is a indicator. So why this indicator shows different colors in different media? In acid, in acidic medium it shows one color, in basic medium it shows another color. So the reason for this, you have to understand the theory of indicators. First thing, the indicator is a substance which is used to determine the endpoint of the titration. So what is indicator? Indicator is a substance which is used to determine the endpoint in a titration. In acid-based titrations, organic substances, actually these acid-based titrations are acid-based indicators are organic substance. They are weak acids or weak bases, right, are generally used as indicators. So all acid-base indicators are weak acid or weak base organic compounds. They change in their color with certain pH range. So we already discussed it. So each indicator having a specific pH range. So based on the pH range, you choose the indicator for particular titration, right? Now this thing already discussed: methyl orange, methyl red, litmus paper, and phenol red and phenolphthalein. If you see the pH range, just see and observe pH range. Methyl orange 3.2 to 4.2, it color change from pink to yellow or red to yellow, right? And methyl red, so that is red to yellow, 4.4 to 6.5 pH range. Litmus 5.5 to 7.5, and red to blue, right? Phenol red, that means red, this change from acid to base. Okay, this change from acid to base. And phenol red 6.8 to 8.4, yellow to red. And phenolphthalein 8.3 to 10.5, colorless to pink. That means colorless in acidic medium, and base, in base it shows pink color. Its pH range is 8.3 to 10.5, right? So these are the different kinds of acid-base indicators and their pH range and the color changes in respect to media, right? So the question is here, so why these indicators are so different colors in different media? So what's the theory involved in acid-base indicators? So theory of acid-base indicators, the two theories have been proposed to explain the change of color of acid-base indicators with a certain change in pH. So namely Ostwald theory and quinoid theory. So first theory, that is Ostwald theory. So Ostwald theory, according to this theory, the color change is due to ionization of the acid base indicator. The ionized form has a different color than ionized form. So what it explains, actually these all indicators they are ionized in aqueous solutions. In other solutions it can ionize, right? If it ionizes into H plus and indicator minus, that is acid indicator. If it ionizes into OH minus and indicator plus, that is base indicator. So it ionizes. So indicator will exist in unionized form and ionized form. So what it says, it shows different color in ionized form, in unionized form. So that depends upon the in which solution it is present, right? And the second point, the unionized, the ionization of the, just wait, the ionization of the indicator is largely affected in acids and bases, as it is either a weak acid or weak base, right? So that's discussed. So it depends upon in which solution it is present. In case of indicator is weak acid, its ionization is very much low in acid due to common H plus ions, while it's fairly ionized in alkalis. Similarly, indicator is weak base, its ionization is large acids and low in alkali due to OH minus ions. So what it explains, so it I'm telling, so it shows different colors in different medias, right? In acidic medium it shows one color, in basic medium it shows another color. That means it ionized if it is ionized in acidic medium and ionized in basic medium, right? So that depends upon the solution it is present. I will give you example if you, so that you can understand easily. So I am taking here a phenolphthalein, right? So consider two important indicators, that is phenolphthalein, that is weak acid indicator, and methyl orange, that is weak base indicator. So Ostwald theory can illustrate as follows. So first I am taking phenolphthalein indicator. So it can be represented as a HPH because it is weak acid indicator. So it having H plus ions. So it dissociate H plus pH minus. So it ionizes in solution to small extent as HPH, that is H plus and pH minus, right? Just write here pH minus. Now, so what actually? So in unionized form, phenolphthalein exhibit colorless. There is no color. In ionized form, it shows pink color, right? Unionized form colorless, in ionized form pink color. So that is what Ostwald's theory tells. So what it was telling. So the indicator shows different color in unionized and ionized form, right? So here phenolphthalein indicator, I am taking example. Phenolphthalein in unionized form it shows colorless, and ionized form it shows pink color. Now I am just adding this phenolphthalein indicator in a solution. That I am taking conical flask. In conical flask you are taking acid, that let us say HCl, right? So HCl gives H plus and Cl minus. Now in that solution you are adding 1 or 2 drops of phenolphthalein indicator. So what happens? So phenolphthalein indicator dissociate into H plus and pH minus. Already HCl dissociate into H plus and Cl minus, right? Now this undissociated molecule of phenolphthalein are colorless, while pH minus as are pink in color in presence of acid. So I am taking HCl solution. The ionization of HPH is practically negligible because now here observe common ion effect, right? So because pH phenolphthalein having H plus ion and HCl also having H plus ion. Now reaction towards left side. So it reaction towards left side means unionized. The phenolphthalein remains unionized. So unionized form, in unionized form phenolphthalein shows pink, colorless, right? Because of common ion effect. So the second thing, if it is present in a base ionization of alkali, for example, if now you are taking in conical flask, if you are taking base, like say NaOH. So in NaOH dissociates into Na plus and OH minus. Now we are adding phenolphthalein, 1 or 2 drops of phenolphthalein indicator. Now phenolphthalein dissociates into H plus and pH minus. NaOH, the ions which are present in that conical flask solution, conical flask is Na plus and OH minus, right? Now there is no common ion here because phenolphthalein indicator having H plus and pH minus, and NaOH solution, that is alkali solution, having Na plus and OH minus ions. So there is no common ion effect here. So here reaction towards right side, that means H plus from phenolphthalein indicator and OH minus ions from NaOH, right? So now here neutralization, here what happens here, neutralization takes place, that is H2O. So here reaction towards the right side, that means phenolphthalein indicator is more favorable to dissociation, right? Ionize, preferable to ionize. So it shows pink color. So that's why phenolphthalein shows colorless, that means no color in acidic medium, and in basic medium it shows pink color. So that is the reason. So I hope you understand. If you take another example, see here color change in solution. Now first thing, phenolphthalein, first if you see the first flask, that is colorless flask, colorless conical flask, and the second one pink, right? So in the first solution is you are taking HCl solution. The first solution you are taking HCl solution. Now you are adding 1 drop of phenolphthalein indicator, in that conical flask. You are having H plus and Cl minus ions. Now you are adding pH, phenolphthalein indicator. Phenolphthalein indicator also dissociate into pH minus and H plus. Here you are observing a common ion effect because H plus from pH phenolphthalein indicator and H plus from HCl solution, though there is 2 H plus ion, that is common ion. So what is common ion effect actually here? So the separation of dissociation of weak acids or weak bases by its own ions. So according to Lee-Chatterley principle, reaction towards left side. So it most favorable in unionized form. So in unionized form of phenolphthalein shows no color, that is colorless, right? So in the second, if you see the second flask, it appears like pink color. So because in that conical flask we are having base, that is Na plus and OH minus. Now we are adding 1 or 2 drops of phenolphthalein indicator H plus and Cl minus, phenolphthalein pH minus and H plus and NaO solution Na plus and OH minus. Here there is no common in effect. Here you are observing neutralization, that means H plus from phenolphthalein indicator and OH minus from NaO solution. So these two are combined and form H2O, right? So it is a reaction towards right side, so most favorable ionized forms. In ionized form, phenolphthalein indicator shows pink colors. So that's why phenolphthalein shows different colors in different mediums. So phenolphthalein indicator shows there is no color in acidic medium. It shows pink color in basic medium. So that is the reason. I hope you understand the things. And second thing, that is a methyl orange. Second example is methyl orange. This is a weak basic indicator. So it is a very weak base and it can be represented as MeOH. So it ionizes in the solution to give methyl plus and OH minus. So methyl orange. So methyl orange I'm taking. So methyl orange in unionized form it is yellow color. In ionized form that is red color, right? That is red color. So in presence of acid, OH minus are removed in the form of water molecules. OH minus are removed in the form of water molecule, because if you are adding this methyl orange indicator add into the conical flask which is containing acid. So acid, let us take HCl solution, H plus and Cl minus. So H plus and Cl minus in the conical flask. Now we are adding methyl orange indicator. So methyl orange indicator which are having the ions Me plus, that is Me plus and OH minus. Now reaction towards the right side, because neutralization process takes place here. Neutralization, because OH minus ions from methyl orange and already H plus ions are there. So these two are combined form H2O, right? So this is neutral. So reaction towards right side. So methyl orange is most favorable to dissociate in acidic medium. So reaction towards right side. So methyl orange which is present in most favorably present in ionized form. So in ionized form methyl orange shows red color. So that's why methyl orange in acidic medium it shows pink color, right? Sorry, red color. And the second, so in the presence of acid, so if you read that pointer, in the presence of acid, OH minus are removed in the form of water molecules and the above equilibrium shifts towards the right hand side. You can reach at the principal reaction towards the right side. So right side, that is red color, and there's a sufficient Me plus ions are produced which is impart red color to the solution. So on the addition of alkali, the concentration of OH minus ions increase in the solution and the equilibrium shifts towards the left side, that is ionization of MeOH is practically negligible. So thus the solution acquires the color of unionized methyl orange molecule, that is yellow color. So if you taking a base, now taking base in a conical flask. Now conical flask we are having base, that is NaOH, Na plus and OH minus. Now we are adding 1 drop of methyl orange indicator. So in conical flask we are having Na plus OH minus ions. Now we are adding methyl orange indicator Me plus and OH minus. Now increasing the OH minus ions. So OH minus are increasing. So reaction towards the left hand side, that is unionized form, that is methyl orange reaction towards the left hand side, that is yellow color. So that's why methyl orange in basic medium shows a yellow color. Okay, right? So what the point is? So methyl orange in acidic medium shows red color. Why? Because in acidic medium reaction towards right hand side, neutralization process takes place. So reaction towards right side, that is methyl orange in acidic medium it is present in ionized form. In ionized form, methyl orange shows red color. Now methyl orange in basic medium is having Na plus and OH minus ions, so increasing the OH ions, strength of OH minus ions, so reaction towards left side, so that is it shows yellow color. So that's the reason of methyl orange shows red color in acidic medium and yellow color in basic medium. I hope things are very clear. Let's see. Here I am having two flasks. So one solution is red color and another solution is yellow color. Now first thing, here I am taking first flask, that pH is equal to 2, that is acid, pH less than 7. So here acid solution. Now first conical flask, that is red color conical flask, we are having acid solution. So we are taking first acid solution, that is colorless. Now we are adding methyl orange indicator. So while adding 1 or 2 drops of methyl orange indicator, the conical flask appears like red color. So because that in that conical flask we are having H plus and Cl minus ions, now we are adding methyl orange indicator, Me plus and OH minus ions. Now H plus from acid and OH minus ions from indicator, methyl orange indicator. So these two are combined, they're forming neutralization. Now reaction towards right side, that is methyl orange is ionized. So in ionized form, methyl orange shows red color. That's why that flask appears red color. The second flask yellow color. So in that conical flask we are having a basic solution, because base solution, that let's say NaOH solution, Na plus and OH minus. Now we are adding 1 or 2 drops methyl orange indicator, Me plus and OH minus. So OH minus, increasing the strength of OH minus ions, reaction towards left side. So that methyl orange indicator will exist in unionized form. In unionized form, the methyl orange shows yellow color. So that's why that flask appears while adding 1 or 2 drops of methyl orange indicator. Here shows that flask appears yellow color. So that's the reason of why methyl orange indicator shows red color in acidic medium, and why it is yellow in a basic medium, right? So next, and the second theory, that is quinoide theory. So that's the first theory, that is Ostwald theory. So in Ostwald theory, that methyl orange, all acid base indicators are weak acid or weak base indicators, so they are ionized. So that indicator in ionized form and unionized form shows different colors. In ionized form it shows one color, in unionized form it shows another color. Now so in which color that shows, that depends upon the in which solution it is present, right? So that's about Ostwald theory. And the second theory, that is quinoide theory. So quinoide theory, so what it explains, according to quinoide theory, acid base indicators exist in two tautomeric forms having different structures with which are in equilibrium. One is termed as benzoyl form, another one is quinoide form, right? So all these acid base indicators are aromatic organic compounds. So they shows tautomerism, that is all these acid base indicators shows two tautomeric forms. What are they? That is benzoyl form and quinoide form. The first thing, first form, that is if you see the top, the first form is a benzoyl form, and the second form, that is it can be rearranged into the quinoide form. So first form is benzoyl form and quinoide form. So two forms have different colors. The color change is due to interconversion of one tautomeric form into others. So one form mainly exists in acidic medium, other form in alkali medium. Thus during titration, the medium changes from acidic to alkaline or vice versa. The change in pH converts the tautomeric forms into other, and thus the color changes occurs. So what it says, the acid base indicators are organic compounds, aromatic organic compounds, it having a benzene ring. So it exists in two tautomeric form, that is benzoyl form and quinoide form. So these two forms having different colors. In benzoyl form it shows one color, in quinoide form it shows another color. Now Now adding one solution to the another solution, we are adding acid to the base. Now medium will change, right? So if it is having base in conical flask, now adding acidic acid solution, so it converts, slightly converted into the acidic medium. Now acid changes simultaneously, it can be converted into the another form, that is quinoide form. So in different mediums, in acid form it exists, in benzoate form, in quinoide form exists in base. So in different medias it exists in different forms, right? So that's the second one. During titration, medium changes from acidic to alkaline or vice versa. The change in pH converts the tautomeric form into other. So in benzoate form it having one color, and in quinoide form another having another color, right? So if you take an example, phenolphthalein, so has been, so that is the structure of phenolphthalein structure. If you see that, the structure of phenolphthalein. So phenolphthalein, I'm already told you now, phenolphthalein is a weak acid, so it having H plus ions. It dissociate into H plus and pH minus, right? So from acidic medium, benzoate form in acidic medium, phenolphthalein has benzoate form in acidic medium, and thus it is colorless, while it has quinoide form in alkaline medium, which has a pink form, pink color. So phenolphthalein has benzoate form in acidic medium. So in acidic medium, phenolphthalein has benzoate form, so it is colorless, while in alkaline medium, phenolphthalein in alkaline medium, this benzoate form will be converted into quinoide form. So quinoide form. So in phenolphthalein quinoide form shows pink color, right? See here, OH and OH. So it dissociates into O minus and H plus. So by arranging this O minus, that negative charge of oxygen we shift into the carbon and oxygen, they form a double bond. So after arrangement, they may be converted into the tautomeric form, that is quinoide form, right? So methyl orange indicator, taking second example, that is methyl orange indicator has a quinoide form in acidic solution and a benzoate form in alkaline solution. So methyl orange has a quinoide form in acidic solution, that it shows a red color, and a benzoate form in alkaline medium. So the color of benzoate form is yellow, while the quinoide form is red. So methyl orange also shows two forms, that is benzoate form and a quinoide form. So in benzoate form, the color of benzoate form is yellow. If it exists in benzoate form, that color is yellow. So that is in basic medium. So while that in quinoide form, that is red color. So methyl orange has quinoide form in acidic medium, so it shows a red color. Got it? In methyl orange has benzoate form in basic medium, so it shows a yellow color. So that's the point, right? So I'm repeat. So methyl orange has a quinoide form in acidic medium. In quinoide form, methyl orange shows red color. That's why methyl orange in acidic medium shows red color, right? In methyl orange and benzoate form in alkaline, methyl orange has benzoate form in alkaline solution. So benzoate form of methyl orange, that is yellow color. So methyl orange in basic medium shows yellow color, methyl orange in the acidic medium it shows a red color, right? So that's about theory of indicators. We are discussing two theories, that is acid Ostwald theory, and second one quinoide theory. So in Ostwald theory, ionized form indicator, unionized form shows different colors in ionized form and unionized form. In quinoide theory, it shows different colors in benzoate form and quinoide form, right? So that's about theory of indicators. And next, types of acid-base reactions. Mainly you are having different types of acid-base reactions. That is a strong acid and a strong base. So what is strong acid? It undergoes complete ionization. It ionizes complete ionization, that is strong acid. Partial ionization, that is a weak acid, right? In the same base also, right? So first reaction, that is a strong acid versus a strong base. Strong acid is HCl, it completely ionizes into H plus and Cl minus. NaOH also completely ionizes into Na plus and OH minus, right? Now strong acid with a weak base. Second one, strong acid, that is HCl, a weak base ammonia, that is ammonium hydroxide we are taking, ammonium hydroxide, and a weak acid with a strong base, weak acid, that is acetic acid, and a strong base, that is NaOH, right? And the fourth one, weak acid with a weak base, that is acetic acid and ammonium hydroxide. You are having four different types of acid base reactions, acid base titrations. Now you have to choose indicators, selection of indicators, that's very important. You are not using same indicators with all these type of titrations. You are using different indicators to the particular titrations, right? The first thing, first acid base, acid and base. So acid, strong acid and strong base, strong acid and strong base, both are strong, that is NaOH and HCl. Strong acid, that is HCl, and strong base, that is NaOH. Both are reacting, which gives NaCl plus H2O neutralization. H plus from HCl and OH minus signs from base, that is NaOH. So both are reacting from neutralization reaction. Now both are strong, so the equivalence point, that is the end point, may appear at pH is equal to 7, around 4 to 10, in between, that is 7. So pH indicators, that means we are using any acid base indicator for this type of titration, that is acid base, strong acid, strong base. You are using methyl orange or methyl red or phenolphthalein. So you can use any acid base indicator for this particular titration, that is strong acid versus strong base. And the second one, strong acid and weak base. Strong acid, that is HCl, and weak base ammonium hydroxide, NH4OH, HCl plus NH4OH, which gives NH4Cl plus H2O. So here strong acid and weak base. So here strong acid. So strong acid, so equivalence point, that is end points lies at pH less than 7, that is acidic medium. The end point lies at pH less than 7, that is acidic. In acidic medium we are getting end point for this particular titration, that is strong acid versus a weak base. So you are using a acidic indicator, that is pH less than pH range, those indicators which are having a pH less than 7, that is methyl orange and methyl red. These two indicators are suitable for this particular titration, that is strong acid versus weak base. And the second thing, third one, weak acid and strong base. Weak acid, I am taking acetic acid, that is CH3COOH, and strong base NaOH. So both are reacting, they form sodium acetate, that is CH3COO Na plus H2O. So here having strong base, so the end point, that's equivalence point, observed at pH greater than 7, because of strong base end point at basic medium, in basic medium. So pH greater. So you are using, you have to use basic indicator, that is a pH range greater than 7, that is 8 to 10.3, that is a phenolphthalein indicator you have to use for this particular titration, weak acid and strong base. Now weak acid and weak base, so fourth titration, weak acid and weak base. So this is in this particular titration you are not observing sudden endpoint, sharp endpoint. So this type of titrations are not performed because you are not observed sharp endpoint. So most often you are using phenol red indicator for this titration, right? Thank you. In the next session, we are going to discuss second type of titration, redox titration. Thank you.